So again, I think some of this is review, but I know different ones of you have seen different amounts of divide and conquer. So the basic idea with divide and conquer is that you break a problem into subproblems, then you go and solve some of those subproblems, and based on what you find in those subproblems, maybe you have to do some extra work in order to get a final answer. And so the super standard example of all of this is always merge sort. The other one that you've probably seen is binary search. Binary search. Solve one problem of size n over 2. Right, so binary search is the problem of finding something in a sorted list. Actually, why don't I why don't I go and we've done a lot of sorting in this class. Why don't I just do the binary search example? So the binary search example, which again, I think a lot of you have seen this before, but you have a sorted array. So like 10, 18, 21, 68, 90, 1012, 1, 2, 3, 4, 5, 6, 7, 8, maybe like 5,000. So the question for binary search is just, for example, is say 15 in the sorted array. Or actually, let's say 100. Is 100 in the sorted array? So brute force is order n. Loop through the entire array. On the other hand, there's a better way. So the better way of solving this problem is the divide and conquer, is to go and split the array in half. Is the thing I'm looking for bigger or smaller than the middle item in the array? So the middle item in the array here is 21, I believe. No, not what I wanted to do. So 21 is the middle number. So I would take the number that I'm looking for, which is say 100, and I would then go and compare the number that I'm looking for with the middle item in the array. And so if what I'm looking for is bigger, search the right half. Else recursively search the left half. Okay. Search, yes. So the number that I'm looking for is bigger. The number that I'm looking for is bigger. So because the 100 is larger than 21, I would go and search the right side. And I would just keep recursively splitting the list in half, splitting the list in half, splitting the list in half. And so I split to get 2 subproblems of size n over 2, but then I only need to solve one of them. For the particular case of binary search, I break the problem into a left side problem and a right side problem, and then I only go and solve one of the 2 problems. And this was the same case when we looked at median finding earlier in the term. Median finding was a bit more complicated algorithm, but the idea was the same, that you go and break it apart into two subproblems, and you only solve one of them. So, right. Alternatively, in merge sort, we split to get two subproblems of size n over 2, and then we need to solve both of them, right? So the right, so this is right. Merge sort is split the array in half, sort the left side, sort the right side, then merge the two sorted lists. So the point that I'm trying to make here is that in a divide and conquer situation, sometimes you're going to be solving a different number of subproblems. Sometimes it's like split it in half and solve two subproblems. I have seen algorithms, I'll see if I can come up with an example of this over the weekend. I've seen algorithms that are like split the problem into 3 pieces and then solve 2 out of the 3 pieces. Yeah, but you basically you break the problem into like break it in half, break it into thirds, break it into fourths, and then you solve some number of those subproblems. So anyway, I think you've probably seen divide and conquer before. We've talked about it a little bit before in this class. But are there any questions about the high-level paradigm? So the thing that I wanted to talk about today a little bit more generally is runtime of the runtime of divide and conquer algorithms. So basically, in a divide and conquer algorithm, you have this recursion tree. So there's like the main problem, the subproblems, they have subproblems, they have subproblems, and eventually you get down to your leafs, which is like this is like sorting a sorting a list of size 1 or a list of size 2. So these are things that you just, once you get down to the leaf, you just brute force it because you're searching for one item in an array of one element, or you're trying to sort a list of just 1 or 2 things. So down here we do brute force, and everywhere above the leaves we go and like split and do some subproblems. And again, like I was trying to say with merge sort, so with like merge sort, where do I see if I can get some text here? So in the case of merge sort, what I would do is I would go and solve this problem, and then I solve both of these problems, and then I end up solving like every one of the leafs. Alternatively, if I'm instead doing binary search, for binary search, my tree isn't quite as bushy. It's just not as big, because for binary search, I just go and only look at, let's say, oops, yeah. So for binary search, I'm not solving everything. I end up like, I end up solving a much smaller section of my tree in binary search. And this obviously affects the runtime. But when we're talking about runtimes of recursive algorithms, I think that this is the right picture to have in mind. That you have the like, oops, not good. Yeah, so that so this is the like Leaf's brute force, and up here we have the this is the like root is the problem we start with. Okay. So any case, I think we've drawn these type of diagrams before, but I just wanted to refresh your memory as far as like, I think thinking about this recursive tree where like this is sorting the whole list, this is sorting the left half, sorting the right half, da 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 da. This is sorting just like one or two elements, one or two elements, one or two elements. And again, how you write your base case, whether your base case is 1 or 2 or 3, depends a little bit on the problem. So then let's get to page break. So runtime of divide and conquer algorithms. So in general, when we talk about runtime of divide and conquer algorithms, so in general, we have the following type of recurrence relation. These are often called recurrence relations, which is typically how we think about the runtime of recursive algorithms. So typically we have that, so T of n is the runtime for an input of size n. And typically what we have is that T of n is equal to A times T of n over B plus f of n. So what this means in general, that so n is the size of the problem, A is the A is the number of subproblems that you solve, and B is the fraction is yeah, so like I guess n over b. N over b is the size of each subproblem, and then f of n is the work to split up and recombine. So basically, like for merge sort, let's actually do the merge sort example. So for merge sort, we have that the time to sort a list of size n is I need to go and solve 2 problems of size n over 2 plus, so this is like solve 2 problems of size n over 2, and then O of n work to merge recombine. Similarly for binary search, we have here T of n is equal to 1 times T of n over 2 plus 1. So this is like solve only 1 problem of size n over 2, and then O of 1 work to split recombine. Right, that for binary search, splitting things, there really is no recombining in binary search. Once you get to the bottom of the tree, there's no work to go and recombine things. In order to split in half, all you have to do to split in half is grab the middle item in an array, and getting the middle item in an array is constant time, O of 1 time. So do these types of recurrences make sense? Any questions on these types of recurrences for talking about divide and conquer algorithms?
I have a question.
Sure.
So for merge sort, how do we prove that this is equal to n log n?
Aha! Excellent question, which is exactly where I'm headed. So, yeah.
Okay, thank you.
So, yeah, exactly where I'm headed. So let's go and insert a. So this is okay. Okay. So we have the recurrence. How do we figure out the runtime? So the idea here, and I think I'm so note, I'm not going to do a full proof. So I'm not going to do a full proof, but there is one in the book in chapter 4.5. So I don't need you to understand. You don't need to understand the full proof, but you should understand the how to use this approach. So this approach is generally called the Master Theorem. I have no idea why this is the Master Theorem for recurrences. I don't actually know why this is called the Master Theorem. Yeah, maybe I can figure that out at some point. But basically, the Master's Theorem says there are fundamentally three types of divide and conquer algorithms. So type one is is there chat? Yes. Excellent. So the divide and conquer algorithms. Yeah, there's fundamentally three types of divide and conquer algorithms. There's the let's see. There's ones where the tree is really bushy wide. So this is like tons of leaves, and all of the work and most of the work is done at the leaves. Then there's also ones where you there are also divide and conquer algorithms where the the ones where the tree is skinny, not many leaves. The tree is skinny, not many leaves. Leaves. Not many leaves. Most of the work is done in splitting, recombining at the top. And then there are ones where every level of the tree has roughly the same amount of work. So this is like kind of the Goldilocks case, right? So, right, the Master Theorem is, right, this is like Goldilocks. Either you have trees that are like too wide and all the work is done down at the leaves, or you have trees that are too skinny and all of the work is done, or not, most of the work is done splitting and recombining at the top. Or you have cases where the tree is kind of like balanced in between, and you do about the same number of work, same amount of work on each level. So like the kind of, this is the merge sort is like the canonical like balanced case, and I'll go more into like exactly what I mean here, but just for thinking, merge sort is kind of like the canonical balanced case, the binary search where you're able to go and like cross out all of this and like all of this. The like, this is the case that we had like when we were doing median finding. Median finding, doing the tree was pretty skinny, and most of the work was done in like pivoting at the top. That the top pivot on a list of length n was where most of the work was done. And then like the other case, the final case, is like the which I don't have enough circles for. Maybe I can go and get myself extra circles. Select this. We'll just so this is and I don't have a great example off the top of my head. I don't have a great example for the like tons of leaves case, but I will come up with one of those for you next week for the tons of leaves case. It's a little bit less common that you end up with like tons and tons of leaves, but there are cases. I'm sure I can come up with something. Yeah. So what the Master Theorem tells us is that if the tree is, so this is like case one, the tree is really bushy wide. So in particular, you have like T of n is equal to A times T of n over B plus F of n. And this case, you end up with a really wide tree if A is big compared to if A is big compared to B. Yeah, so so this is like think of this as the A is big case. So let T equal okay, let's see if I can explain this. So all the Master Theorem, figuring out what case we are in the Master Theorem is always based on this key value of log A over log B. So if A is much larger than B, then log A is going to be bigger than log B, and this key value is going to be large. So basically, you should think of like n to the this is not really this is, yeah, like, so n to the key is Yeah. So so where does this log A over log B come from? This log A over log B comes from if you try to figure out how many leaves are there in the tree. The number of leaves in the tree is basically going to be n to the key, or it's going to be like on the order of, is roughly on the order of the number of leaves in the tree. And I'm not actually going to work through the math here, but like the math is in your textbook if you're interested. Oh, the other thing is that if you're interested in this kind of stuff, note that this is the this is also the log base B of A. Yeah. So this is the number that you have to raise B to in order to get A. And it's a rough measure of like how much the tree is branching, and n to the key is where this is the key value. N to the key value is roughly the number of leaves in the tree. So if f of n is O of n to the key, this means that so this means that f of n is small. This is like the A is big case, or the f is small case. So f of n is small compared to the number of leaves in the tree. And remember, like fn is the amount of work you're doing at the top in order to initially like split, pivot, recombine. Fn is all of the work that you need to do that is not recursion. So remember, for binary search, this was like tiny, because in binary search, it only takes constant time to go and split a list in half. But for merge sort, we needed to do some recombining. For median finding, we needed to do some pivoting. So all of the stuff that is not recursion is captured in this f of n. So if f of n is small compared to the number of leaves in the tree, then let's see if I can get the right one. Yeah, then basically here the overall runtime T of n is just so you remember that theta means like both big O and big omega. It's like bounded above and below by the number of leaves. So this is the like the brute force work. There's a ton of leaves. There's not much work we have to do to split or recombine. There's a ton of leaves. And so the brute force work that we do to process each leaf dwarfs the splitting and recombining. This is case one of the Master Theorem. So again, I want to go through the three possibilities here for the Master Theorem. I don't expect you to like memorize this, but I expect that you should be able to, you should be aware that the Master Theorem exists, and you should be able to look this up and use it if you're ever creating divide and conquer algorithms. So then, if that's case one, case two is the other extreme. So Case 2 is the other extreme, which is the tree is really skinny. So again, we have T of n is A times T of n over B plus F of n. Think of this as the case where A is small or the F of n is big case. Oops. So again, the master theorem, we always look at this same key value, log A over log B. So this is, again, n to the key is roughly the number of, leaves in the tree. And then this is the case where F of n is omega of n to the key. So this means that F of n is big compared to the number of leaves in the tree. And in this case, the overall runtime of T of n is just the overall runtime. T of n is just beta of okay. I'm not going to go into a ton of detail here, but this is the case, just to remind you, this is the median finding case. Essentially, all of the work effort is done for the initial pivot. Once you've done the initial pivot was like looking through a whole list of size n. And once you've done the initial pivot, then everything else is easy because we're like throwing away big parts of the tree. And done in the initial, So so this is case 2. There's a technical caveat here that, again, if you're interested in the mathematics behind this, there's a lot of really ugly functions in the world. You might remember at some point that I gave you a homework problem where I was asking you to come up with like ugly functions that were neither big O of a polynomial nor big omega of a polynomial, like these weird functions that just like zigzag all over the place. If you go with a really ugly function like arctangent, there's a lot of ugly functions in the world. Ugly f of n's will break this case. Most of the time, f of n is like n or n squared. Like most of the time, this isn't a problem, but I feel like I need to include that caveat. And then finally, case 3 is the Goldilocks case. Tree is nicely balanced. So the idea in case 3 is that you're doing about the same amount of work at each level in the tree. So this is okay. Think of this as the case where you do about the same amount of work at every level of the tree. It's like the Goldilocks case. Again, we have this key value. We have the number of leaves in the tree. This is the case where f of n is both big O and big omega. F of n is like tightly bound. It's like exactly end of the key. Yeah. F of n is like exactly end of the key. Wonderful. What does this mean? Yeah. This means that f of n is the work done at the top for the initial split / recombine, and end of the key is the amount of work to process every leaf. So work at the top and work at the bottom are about equal. Okay, and this means that right. So overall runtime is just grab this. So this is the case where you get an extra factor of log n. And this is the merge sort case. Yeah. So yeah, anyway, this is the merge sort case. Yeah. You do about n work at each level of the tree, and there are like say log n levels in the tree. Okay, so in any case, this is the this is the Master Theorem. This is the #1 tool that we have for figuring out, this is the #1 tool that we have for figuring out what the runtime is of divide and conquer algorithms. And I guess I should put in one caveat here. The third case can be generalized a bit if f of n is theta of n to the key times log n. If you look this up in the textbook, they add in this extra generality, I believe, of but the middle case still works even if you have some logs sitting around. Basically, the middle case says however many logarithms you have sitting around in F, just add another one. So merge sort was T of n equals 2 times T of n over 2 plus n. Case 3 also works for so basically what case 3 says is add a log. So if you're basically case 3 is, if like in merge sort, if you start with an n, you go and add a log. In case 3, if you already have a log, go and like add another log, so log times log. So this just generalizes things a little bit. Again, I don't expect you to memorize the Master Theorem, but you should, if we're going to work through some examples next week, and there will also be an example on your homework of a divide and conquer algorithm. And if you have a divide and conquer algorithm, you should be able to use the Master's Theorem to figure out which of the 3 cases you're in and what the runtime is. So this is a useful tool for understanding the runtime of divide and conquer algorithms.
I have a question.
Yes.
Is every dynamic programming question or a problem is a divide and conquer, but not vice versa?
So the so this is the relationship between let me actually put okay. So insert, so the relationship between divide and conquer and dynamic programming. Yeah, so the way I think of this is that divide and conquer is a broader, more general category. One way to think of this is that dynamic programming is a subclass of, or a subset, subset of divide and conquer algorithms, or divide and conquer algorithms, where you really don't want to do recursion. Okay, so so one way to think of this is that that is dynamic programming problems are divide and conquer problems that have so many leaves in the tree that you wouldn't want to that it would be super slow to recurse all the way down, and so you want to do something more clever. Clever, remember the solutions to subproblems. So dynamic programming is like a special case of divide and conquer, where you have an absolute ton of leaves. So you have so many leaves that, but fortunately, the same subproblem gets solved, like appears multiple times in the tree. So dynamic programming is a particular way, it's a clever way of dealing with, the idea in dynamic programming is this idea of remembering the solution to subproblems that you've already solved. Now, merge sort, like, note, so for merge sort, not helpful to remember that 3, 8, 4, 2 sorted is 2, 3, 4, 8. Because probably this doesn't come up very often. Okay. So like merge sort, the dynamic programming idea of like saving the answer to problems you've solved before is not very useful, because remembering that this sorted is this is probably not helpful, because your list that you're trying to sort probably has this this sequence is only appearing once. Now, I mean, like, I don't know, maybe like, so typically in sorting, you're not asked to sort 3842, 3842, 3842, 3842, right? That doesn't typically come up very often in sorting. But in the dynamic programming problems that we looked at, the same subproblem could come up over and over again, and so saving the answer actually makes it faster. Okay. Any other questions?